Good morning, everyone, and welcome to the awesome four-part series we're calling Getting Schooled by Siggy with one of our industry's best-known engineers and teachers, John Siegenthaler, DE. John has been a 35-year trade professional and has a passion for water-based engineering, and he's sharing that passion with us today. So I'm your host, Dan Ashenden, group publisher of BNP Media's Mechanical Plumbing Group, which includes our three well-known brands, which, of course, John writes for. And the first is Plumbing and Mechanical, which is the #1 brand for contractor-focused contractors. And the second is PM Engineer, the leading voice for PM engineers. And then Supply House Times, which is the official publication and brand of the ASA for wholesale distributors. This webinar series is brought to you by Caleffi North America with their outstanding hydronic solutions. Caleffi's partnered with BNP Media to offer you this complimentary four-part mini-series presented by Siggy. Siggy's main topic is how to design, construct, and commission hydronic and heating and cooling systems that leverages today's low-energy using technology while keeping things as simple as possible. Comfort and high efficiency, as we all know, equals a happy customer. Today's plan is part 2, and that's covering heating and cooling sources. And that means geothermal, air, and water sources for heat. And John will be covering that in detail today. And then there's 2 more parts, of course, for the next following Tuesdays of June 16th and June 23rd. You will receive a certification of attendance today, emailed to you for your continuing education efforts. And so without delay, I want to switch it over to Siggy, but first I believe we have Hot Rod Ward to give us some housekeeping details. Hot Rod, are you there?
Yeah, I am, and thanks for the nice intro, Dan, and for kicking us off. So a couple housekeeping slides here, the typical stuff about connections. If you're having a staticky connection or an echo or a problem like that, sometimes you can just, close it out and log in again, and that goes away. In fact, we had that problem with our own crew this morning. We had to log it in and out a couple times to get things cleared up. So yeah, the episodes, as Dan mentioned, will be archived as a YouTube on our. It takes us a couple days or a week to get that posted up there, but you'll be able to view them again or review them if you want. So I think that's it on this slide, Siggy.
Yeah, thanks, Hot Rod. And again, I want to thank BNP Media for partnering up with Caleffi to sponsor this 4-part mini-series. We had a lot of fun putting this together, and hopefully there's a lot of good information coming. And speaking of information, I just want to mention a resource that some of you may be aware of, others may not. Last year, I worked with BNP to do a compilation of about 340 articles. And these are articles, as Dan was mentioning, from Plumbing and Mechanical, PM Engineer, Supply House Times, going way back to July of 1996. And this is a free resource. If you go to either the Plumbing and Mechanical website or the PM Engineer website and look under the Multimedia tab, you can get a link to this. And it's, again, it is online, it's free, and there's just a lot of information there. And you can go through and search and glean details for hydronic systems there. So that's one of the resources. And then I'm going to throw it back to Hot Rod to tell you a little bit about another resource here.
Yeah, thanks, our Hydronics. Hopefully everybody's receiving these hard copies. You can go to our website and sign up for these if you're not receiving them. It's a free publication twice a year. We mail it out, but something exciting coming up with Hydronics. We're going to, I guess, virtualize this and have a smart version of this for the next issue that's coming out. So we're just working on the details. And that there'll still be a hard copy being mailed out, but we're trying to make it more readily available for people that are still at home and that. So look forward to that. But the next issue actually is on the topics that Siggy's presenting today, so it kind of ties in nicely when you see that. I think all the slides and information that you'll be seeing over this series, Siggy, pretty much will be represented in that next Hydronics.
It will be a lot of good details in there. So let's jump right into it. Episode 2, just a real quick recap. Last week we took a look at an overview of the project. This was a new low energy house that was built for my daughter and her husband. And it incorporates a lot of different hydronic details. And today we're going to start to drill down into some of the nuts and bolts of those details. One of the things that's, I guess I'd say, unique about the project, there's 2 heat pumps on this project. There's a geothermal water-to-water heat pump, which is something my son-in-law really had his heart set on. We had the land area to do it. And so we do have a geothermal water-to-water system, and that's, I guess I'd say, our planned heat source and also our cooling source. But as we were going through the project, we had opportunity to make this house a test bed for a new air to water heat pump, a space pack product. It's a low ambient split system air to water heat pump. And the original plan, going back about 2 years ago, the original plan was to back up the geo heat pump with an electric boiler. If we had any service issues with that, we could just, we could use the electric boiler as a second stage. But we decided to abandon the electric boiler because basically we had a second heat pump. So I'm going to show you how we set these heat pumps up. They're basically set up as a 2-stage system, and we can select which heat pump is the lead stage, and of course the other one would be the lag stage, and it's just a matter of using a switch to determine which one goes first. And we'll look at how they come together piping wise and control wise. They both basically send the energy either in the heating mode or the cooling mode into a buffer tank, and then the buffer tank is kind of the launch pad for all the different loads that are on that system. And again, today we're going to look at that source side, and on episode 3 next week on Tuesday, we're going to get into all the different heat emitters. And in episode 4, we'll get into the controls, we'll get into any other remaining details, and even some simulation of what the performance of this system is going to be. So last week I showed you this schematic, and I made the comment, boy, it looks pretty complicated. How does the water know where to go? You see there's a lot of different devices here. Circulators, buffer tanks, heat pumps, panel radiators, radiant floor circuits, heat exchangers. So today what we're going to do is we're going to basically look on the left side of that buffer tank. We're going to look at the air to water heat pump, and that's the outdoor unit of the split system. We're also going to look at the water to water heat pump. And then finally, we're going to take a look at how do we put the pipe in the ground for that geothermal loop. And one of the things I want to encourage you as you're listening today, if you have a question, just click on the box, raise your hand down there, and either Mary or Hot Rod, I'll just pause, and if we have questions coming in, we can pause, and we can turn on your mic if you'd like to ask that question directly, and hopefully we'll have some time at the end to entertain questions as well. So don't be shy, jump in there. It's a good opportunity. If you see a detail or have a question about anything on the relevant to what I'm showing you, let's address it. Okay, so we're going to start off with the water-to-water heat pump, and we selected a unit here. It's a fairly typical type of unit. It's a nominal 4-ton water-to-water heat pump, and it's a 2-stage unit. And in a 2-stage unit like this, you have a scroll compressor and you have a bypass solenoid valve. And essentially on low capacity, when we go down to the lower speed, we're going down to a nominal 3-ton machine, which in this particular project matched up really well with our cooling requirement. All that happens is some of the refrigerant bypasses the compressor. Okay, so we don't have as much of a vapor compression effect going on. So in a sense, we're just taking away about 25% of the capacity of that heat pump using that bypass valve. And we selected that because, again, we needed the full 4-ton capacity. One of the things that I mentioned last week, but again, we'll get into it in a lot more detail next week. The garage on this house, it's a 3-stall garage. It's 24 by 32. It has floor heating in the slab, but we're not necessarily going to keep that garage heated all the time just to conserve energy. If we do turn that slab on and it is cold, some of you know that turning on a cold slab puts a very high transient load on the system. And so we wanted to have a heat pump that could address that load. In fact, with 2 heat pumps now, we can actually have on the order of about 8 tons. If both heat pumps are running, and we have tested the controls and have been able to confirm this, we can actually have up to 8 tons of heat input going into the system. And what that does is it allows that slab to come up to temperature without literally draining the BTUs out of the rest of the system and causing discomfort in the house. So the water-to-water heat pump, you can see it down here in the lower right. It's roughly about 2 feet high, 2 feet wide, and that's about just under 2.5 feet deep. Sheet metal cabinet. You see all the piping is lined up over here on the left side as you face it. These 2 pipes go through the wall. They go back to the earth loop. The other 2 pipes work their way over to the buffer tank. One nice thing about this heat pump is there's actually 4 surface panels. You can take any of the side panels off of this. And if we ever need to access the compressor, basically it's sitting right here behind this panel. So if you're working with a product like this, you want to plan enough space in a mechanical room to make sure if you ever had to remove and replace that compressor, that you can get to the internal components on this system without having to physically disconnect it. Now the 2 photos up at the top here, that they show basically the upper left side header on the buffer tank. That would be this header right over here on the schematic. And that header is made up with 2-inch stainless steel T's. One of the things that you want to do with a header is keep the pressure drop as low as possible. We're going to actually use this tank not only as a buffering thermal mass, but it's also going to serve as a hydraulic separating device between the 2 circulators that run the 2 heat pumps, if they happen to be on at the same time. And it's also serving as a hydraulic separating device for several different load circuits that we'll get into next week. So the water-to-water heat pump basically is this box right here. It does have a desuperheater in it. We ordered it with a desuperheater for domestic hot water heating. And if you're not familiar with that term, a desuperheater is an extra heat exchanger that takes the hottest refrigerant gas coming off the compressor and basically cools that gas down through what's called its superheat. We're cooling the gas down to the point where we can start to cause it to condense. And we can use that heat that we're extracting from that hot refrigerant to preheat or fully heat domestic hot water. So if you look at the pipes on this, there's actually 6 pipes connected to the left side of that heat pump. And these lower 2 pipes go over to a 38-gallon electric water heater. And that desuperheater will have the hot gas going through it. And there's a small bronze or stainless circulator built right into this heat pump that runs whenever the compressor is on, with the exception that if the domestic water temperature gets up to 130 degrees, that will actually shut off the circulator for the desuperheater. And that's just purely a safety device. So when this machine is running either in heating mode or especially in cooling mode, we're able to get a large percentage of the domestic hot water from the heat pump as opposed to the electric element in the water heater. So that little detail is shown here, the desuperheater and a small stainless circulator. The earth loop we're going to look at in more detail. You'll see that there are 4 circuits here. They're about 950 feet of 1-inch high density polyethylene pipe. This is SDR 11, which is a standard diameter ratio. That means that the ratio of the outside diameter to the wall thickness is 11. This is tough pipe. This is the same type of pipe that would be used for a gas service. And we bought that in 1,000-foot coils. And we were a little conservative in where we turned the earth loop around. You'll see some photos coming up here in a minute. So we didn't quite use all 4,000 feet of it, but the vast majority of it is installed. Some other details that I firmly believe belong in every earth loop. One is an expansion tank. We've actually written about this in Hydronics. If you take a look at, I believe it's Hydronics number 9 on geothermal heat pump systems. The fluids in a earth loop expand and contract, just like the fluids in any hydronic system as they change temperature. And one school of thought is that the piping also expands and contracts. So in a sense, you can say, well, as the fluid's getting warmer, the pipe's getting warmer, and it's going to expand. So therefore, you don't need an expansion tank. If the pipe is expanding and the fluid's expanding, you don't need a tank. Well, that would be that would be true if they expanded at exactly the same rate, and they don't. The piping actually expands faster than the fluid. So what happens is in cooling mode, when the fluid in the earth loop is warm, the piping is expanding its internal volume slightly faster than the fluid is expanding. So without an expansion tank, the pressure in the earth loop can drop literally to the point where you can start to cavitate the circulator. Remember, this is a closed loop system. And in the winter, what can happen is the piping will contract, but it contracts at a slightly faster rate than the fluid, and the pressure can get up to 50 or 60 psi, which in theory doesn't cause any problem. But you may have a joint that might leak or weep a little bit at 60 psi, and it wouldn't if it was at 15 or 20 psi. So putting an expansion tank in an earth loop stabilizes or reduces that pressure change. You're still going to see some pressure variation in the system, but putting an expansion tank in there reduces it. And again, if you want to read about that in detail, check out Hydronic's number 9. We put the math in there to let you size those tanks up. This does have a high performance circulator, high efficiency ECM circulator in it. Anytime we put that into a system, we like to have a magnetic dirt separator. So we've got that in the system here as well. We also have isolation valves on these individual earth loop circuits. And again, you'll see this is a little different from a typical common earth loop application where all the joints are done with fusion techniques outside the building, and there's just 2 pipes that come through the wall. We brought all 8 of these pipes, 4 supplies and 4 returns, through a set of holes in the wall and built an internal manifold. And we'll talk about that a little bit more. Now,
hey, Siggy, you want to
yes.
do a couple questions on that slide while we're there? We had a couple good ones come in. First, Mark asked about, I think what he's saying here is when you mix the panel radiators with the radiant slabs, how does that perform? He said, is there a lag that you noticed on the slab circuits compared to the panels? I think is what he's asking on that. Maybe you can talk about that.
Nothing that causes a problem. I mean, in theory, yes, the floor would have a higher mass to it than the panel rads, but honestly, from experiences with the system, we haven't found that to cause any problem.
Okay.
Now,
then,
one other point I'll make quick on that: when you do mix radiant panels and panel rads, you know, if you can bring the water temperature of both to a common value, you don't have to use a mixing device. You know, if you size the panel rads for 120 and the radiant floor needs 95, that's a big variation. You probably are going to want to use a mixing device. If you can bring them closer together, you can simplify the system, eliminate that mixing. Go ahead, Howard.
Then Daniel asked about glycol, which would play into your expansion tank too, I guess, a little bit. Is there glycol in the loop field?
Yes, there is. It's a 25% solution of inhibited propylene glycol. That's the only antifreeze that I'm comfortable with in a loop. I know some systems have used methanol. Some systems I think have used ethanol, and the other glycol, ethylene glycol. I'm not comfortable with putting, this earth loop. I forget the exact volume. I want to say somewhere in the range of maybe 150 gallons. So we're putting quite a bit of antifreeze in there at 25%, and toxic or flammable materials, just handling the alcohols in a mechanical room, I just don't feel comfortable with it. So, there is no ideal antifreeze. They all have pros and cons, but we went with the propylene glycol on this.
Okay, and then got time for one more.
Sure.
Michael's asking, the expansion tank on the geo loop, shouldn't the connection on the loop be on the other side of the heat exchanger between the air dirt separator and the heat pump?
Well, no, it probably could be. You see the connection here is close to the inlet of the circulator. So that's basically our point of no pressure change. And we're going to get a pressure drop through the earth loop, and we're also going to get a pressure drop through the heat exchanger in the heat pump. So, you know, there's really nothing wrong with where it is. It could be moved, but I would also, if I move the expansion tank, I would also move the circulator so that we're pumping away from the expansion tank connection point.
Okay. I don't know if they just keep rolling in here. Maybe we should wait to the end, Siggy. You want to keep doing them on this slide, or?
I'll go a little bit farther. If we get a lot, maybe we'll pause again, but hopefully we'll have some time at the end. I want to just go back to the water-to-water heat pump specifically. And one of the things that, if you've not dealt with heat pumps before, heat pumps are very sensitive to their operating conditions. And in the case of a water-to-water, they're sensitive to the earth loop temperature, and they're also sensitive to the temperature that is leaving the condenser. This would be the water that's going off to the balance of the system, let's say in heating mode, that's going off to the buffer tank and eventually off to our heat emitters. And for this particular heat pump, I plotted out, this would be at high speed now, full load performance, a graph here. This is heating capacity in thousands of BTUs per hour versus the entering source temperature. This would be the water or the water antifreeze solution entering temperature to the heat pump. You'll see that at 110, the heating capacity is a little bit lower than it would be at 95. And yet you look at that graph and say, gee, that's not a lot of difference. And this tends to be the characteristic. You do go down in heating capacity as the source temperature goes down, and you also go down as the load water temperature goes up. But the difference is not, you know, it's not profound. Look at the graph for COP over to the right, over here. You'll see a much more pronounced difference. And with a heat pump system, we're always trying to maximize coefficient of performance. That would be the ratio of our output energy from the heat pump per unit of input energy. So there's a significant difference in performance if we could operate the heat pump with a water temperature leaving the condenser of 95 versus, let's say, 110. And you know, you can go farther out on the range on the high side too. We can go up to 120, 125 degrees. And what you'd find is that you'd have another curve down here somewhere. So the takeaway on this, and this is just kind of a universal design concept with heat pumps, is you want to keep the water temperature in your system in heating mode as low as you possibly can. So low temperature radiant panels or generously sized panel radiators. If you're using a fan coil, you want it, you know, a big coil with a lot of heat transfer capacity. It is definitely a difference from a boiler. You know, with a boiler, you can push up the aquastat and you can kind of cover up perhaps situations where the heat emitters were, you know, let's say you didn't have enough heat transfer plates or the spacing is too wide. You can compensate for that in water temperature with a boiler. And yeah, you do lose some performance, but with a heat pump, it's really important to focus around that low water temperature. And you'll see this is also the case with an air to water heat pump as well. Okay. And I just threw in here, this is right off the manufacturer's IO manual. You also want to take a good look at the pressure drop through the coils or whatever the heat exchangers are. Some use a coaxial coil heat exchanger, some use a brace plate heat exchanger. Make sure that when you design the earth loop as well as the circulator that's going back to the balance of the system, that you're going to get the flow rate that you need based on the pressure drop through not only the earth loop piping, but the heat exchanger and the heat pump as well. In general, you're going to have more pressure drop in a heat pump than you would have in, well, certainly you would have in a cast iron boiler. They have very, very little pressure loss, but there's significant pressure drop in these heat exchangers, and you have to make sure you take that into account. So you would get that information from the manufacturer, and you'd work that in with head loss calculations for the earth loop, and then basically match it up with a circulator. Okay. Now the earth loop itself, we were generous when we put this in. We could have done this earth loop with probably We have 4 circuits. We probably could have done it easily with 3 circuits, but we looked at it. The excavator that we worked with had a 6-foot bucket, big machine. He can dig fast. The pipe wasn't very expensive, so we made a decision. Let's do what we call a 4/4. So basically, with this you can see this bucket here. This is a ditching bucket that's 6 feet wide. We dug down 6 feet, and we've got 1, 2, 3, 4 pipes at the bottom, nominally 2 feet apart. You can actually see them right here. All right. And then we went all the way out to the end. We made our turn, and the excavator led us back. He put about 2 feet of fill over those lower pipes, and we basically just came right back with 1, 2, 3, 4 pipes, and then we put the rest of the fill in. Down here, you can see we're actually unrolling these 1,000-foot coils of 1-inch pipe. These are heavy. We had to use a chain and the excavator to get these things into the trench. You don't really want to. A couple people can pick them up, but they are heavy. We're actually using landscape staples where we need to hold that pipe in place so it doesn't just move around inside the trench. The other thing I want to point out, in case we have any ocean inspectors watching today, we did back shelf this excavation. The actual grade is about here. So our excavator gave us a nice shelf at about no more than about a 4-foot excavation. You actually don't want to do something like this where you're up against the wall 6 feet deep. I'm sure that's in violation of OSHA, and it's dangerous, especially in soils that have water percolating through them. That bank can break away, and it can pin you, and it can kill you. So you've got to be careful about that. Now, our situation with this earth loop is we had to come out of the northwest corner, and because of where the lot, the shape of the lot, the placement of the leach field, the placement of the well, working around all these different underground utilities, we ended up with a path that looked like this, kind of not a complete circle, but about 270 degrees. And as you go out laying the pipe in something like this, think about it, you're using more pipe on the outer radius of this trench than you are on the inner radius. It's just a longer distance. So what we were originally thinking about, the original plan was to get out to the end of the ditch and do U-turns in a vertical plane, where we would dig down a little bit deeper. We would take the pipe and just literally imagine each coil in its vertical plane. We would do a U-bend, and then we would come back at the 4-foot depth. Well, that's going to leave quite a distance variation in these loops. And actually, it was our excavator, Wayne Heides, the guy I've known since he was 18 years old. He's done work for us for 40 years. He said, well, let me dig you a shelf out here at the end. And you can see what he's doing here. This is where he's transitioning up from the 6-foot depth, and this is where we're going to head back at the 4-foot depth. And basically, we got a U-turn. So what we did is we turned each coil within that excavation. And what was the, let's say the red circuit here, this was the outgoing pipe at 6 feet. On the outside of the trench becomes the pipe coming back on the inside of the trench at the 4-foot depth. And it just made sense to us that that was going to compensate. And it actually did very well. When we got back to the building, each of these loops was within about 2 feet of the length of the other loop. So we had essentially equal lengths. We wanted to be absolutely certain that we'd make it back to the building and obviously get through the wall with a little length of spare. So we did turn around a little earlier than we had to. We didn't use, we probably could have gone another 20 to 30 feet with the length of this, but we've got plenty of pipe in the ground for the requirements of that heat pump. So that was kind of a novel solution. I did do an article on that last year in Plumbing and Mechanical, and my hat off to Wayne, our excavator, for making a really smart suggestion on how to turn those loops around. One thing I also want to stress, as you're placing pipe like this, you make sure you uncoil it. Don't pull it off the side of the coil. I'm sure any of you that have worked with radiant tubing know that. Same thing here. You basically need to keep these coils vertical. It's a bit of a wrestling match going out through there. A couple people can handle it, but you don't want to. You definitely don't want to start pulling pipe off the side of the coil. You'll end up fighting it. Basically, it'll be impossible. So make sure you unwind it just like you would rolling a tire down through that trench. And you can see in our trench here, we definitely had water weeping in. This is a clay soil, a few veins of gravel once in a while, but we were working in a mud good portion of the day there. And we actually put all that pipe in and covered it up in about 5 hours. So it went well. Now, let's talk about getting that pipe through the wall. We want to try something here that I had not done before, but it seemed like it would work, and it actually did work very well. I went on eBay and I found a source for solid polyethylene rods, and you can buy these in different lengths and you can find them in different diameters. So we bought 8 rods, those white cylinders that you see this fellow holding here. These are 3 inches in diameter and they're exactly 8 inches long, and they're just solid plastic. So what's going on here is the outer form of the wall is in place. That's that black background. He's holding these in position, and there's somebody on the outside of the wall with a impact driver and screws. I mean, basically just put some deck screws right through the forms to hold those in place. And of course, once that inner form goes in place, we're going to screw them in there as well. So these are going to create voids that are 3 inches in diameter in the wall. And with polyethylene, the thought was the concrete won't stick to it. We actually sprayed a form release agent down into the forms, standard practice to make sure the forms themselves don't stick. And this is what it looks like when we strip the forms off. So you see the rods are in place. There's actually a couple screws still left in here. They pull the forms out, rip the screws right through the forms. But you can see how this worked. It worked pretty well. So we've got our 4/4 pattern. The concrete was all placed with an aerial boom. It was just given this project, the slope of the grade and so forth, that was the only practical way to get the concrete into the form. So at one point, that aerial boom was stretched out 105 feet, and the operator was keeping a close view on the pads, making sure he wasn't going to tip the truck over. So here's the train. We got the guy holding the hose. He walks down the form. Here's the guy that is actually the head mason. He's got the end of the vibrator, and then the guy behind him is actually holding the mechanical part of the vibrator. And basically, these guys just walk down the form. First guy puts the concrete in. The next guy runs the tip of the vibrator down in there to make sure that that concrete settles properly into the form. And these guys all have really good balance. I was very impressed. So this is the concrete contractor's son. I think he was maybe 12 years old. He took out his hammer, tapped on those polyethylene rods, and they pop right out. And you can see that leaves a nice smooth hole. We didn't have to get into core drilling. We didn't have to worry about drilling through some of the rebar in this wall. This wall has 1/2-inch rebar vertical and horizontal at 12-inch spacing, so there's a fair amount of steel in the wall. And rather than just arbitrarily drill holes through there, this worked out really well. Just a couple other shots there. That shot right there actually shows Harvey is putting down some landscape staples just where we needed to. We didn't use these everywhere. We used them where the pipe was fighting us a little bit, just to make sure that we could keep these pipes relatively equally spaced at the bottom of that trench. And the landscape staples, you just tap them in with a hammer. I think they were 6 inches long and 2 inches wide. We didn't, they're relatively loose. We have no concern about them being abrasive on the pipe, anything like that. Now this shows the pipes coming through the wall. We used a product here. I know one of the trade names is Link Seal. There are several other companies that make these, but it's essentially a rubber compression seal that has metal plates and stainless fasteners. And you buy these for a specific hole size through the wall and a specific tube size. Ours were relatively small. we just slid them in place. You can see the tube comes through right through the center. So it's like a rubber donut around the tube. And then you tighten down. In our case, we only had 4 fasteners, and these are all stainless. These are rated up to withstand 20 pounds per square inch of hydrostatic pressure on the wall, which is, if you have 20 pounds per square inch of hydrostatic pressure, the wall probably isn't going to be there very long. Anyway, the tubes all came through. We just trimmed them off. We put some electrical tape over them temporarily, make sure we didn't get bugs and so forth in there. And you can see we also put a drain in that will eventually be a floor drain right underneath this. If we ever did have to change the fluid or service a pump, whatever, it's a good idea to have a floor drain there. Here's a couple shots. This is how we transition from the 1-inch high density polyethylene over to 1-inch copper. We put a ball valve on each of these 8 pipes, and we just got a brass fitting that's 1-inch MPT to barbed. We put 2 stainless steel clamps on, hose clamps on it. And we actually did run this particular wall. There's 2 inches of styrofoam, which you can see here, but then once that slab, that basement slab was in place, there's also a 2x4 wall with mineral wool insulation, 3.5-inch mineral wool insulation. So we want to make sure we weren't getting condensation in the mineral wool. So we used a 2-inch PVC sleeve that goes right back up against the link seal. And that, as you can see, that comes through the wall. The pipe comes through. We sprayed some foam in there. I'm not sure if the foam was critical or not, but we sprayed a little foam in just to stabilize it. And then you can see down here, each of those ends of each earth loop connect through 1-inch pipe, and then the header itself is 1.25 inch copper. Over here on the right, these were a couple temporary fittings just so we could connect the earth. Well, we had borrowed a flush cart to fill this. So we just, if you're looking at that and saying, yes, those are black iron fittings, but they're temporary, they're coming off. There are 1.25 inch FPT ball valves on the end. If we ever have to add fluid to the loop or purge it, we can reconnect some fittings and connect the flush cart up to it. Here's a photo. This is the internal manifold finished. Here's the air and dirt separator. This is the ECM circulator. It has a stainless volute. Everything's insulated except the volute and the air and dirt separator. And this is an area, it's difficult to insulate circulator volutes right now. There aren't a lot of smaller circulators that have insulation shells. It's something I'd love to see more circulator manufacturers look at. Realistically, as we see more heat pumps coming into the market, both geothermal water to water and also air to water, we're going to be seeing more chilled water cooling, as well as earth loops themselves operating well below the dew point of the surrounding air. So without insulation, you are going to have condensation. And one could argue stainless steel doesn't corrode, but you will find corrosion eventually on the flange bolts, even on the handles. So we're still contemplating how we're going to finish that insulation, but we try to be pretty careful with the insulation everywhere else. There's the expansion tank. Got a nice bracket on it here, so when somebody bumps into it, it doesn't break the connection. It does have a ball valve, so we can isolate it if we ever have to change it. This is just a service switch for the earth loop pump if we needed to work on it. And we got a pressure gauge so we can watch the pressure in the earth loop. We did find these plastic connectors, well, plastic support brackets, I would call them. And what happens with these is that foam insulation can actually slide right into the center point. And if you caulk around the seam, you've got a nice vapor tight support. And yet the plastic that this support is made out of is strong enough to hold that pipe. That's 1.25 inch copper pipe. So again, when you're dealing with either chilled water piping or you're dealing with earth loops that are going to operate at temperatures down to perhaps 30 degrees, well below dew point, you want to make sure that you detail your pipe supports so that you have to support the pipe weight-wise, but also detail it so it doesn't have condensation on it. Okay. So we'll switch over now. The other heat pump, as I mentioned, partway through our project, we had opportunity to let this house be a test bed for this unit. It is a space pack unit. I believe it is hitting the market this summer, actual availability on it. This is a nominal 4-ton machine. Here's the outdoor unit. You see the refrigeration line set right here and the safety disconnect for the power. This is the inside cabinet. It's about the size of a ModCon boiler. Here's the refrigeration lines coming in. So we've got the split system in there, and it just pipes into the same header as the buffer, as the water to water. So the water to water heat pump and the air to water heat pump are just in parallel. Either one can contribute heat or chill water to the buffer tank. We made sure we have check valves in there, and this is an isolation and a purging valve. There's actually isolation valves here that don't show. If we had to remove either heat pump, you know, having those isolation valves is a good idea. This shot over here, these are the two refrigerant connections, a 3/8 liquid line and a 5/8 vapor line. This is the outdoor opening where the refrigerant lines are going to go in. These are just temporary caps. One of the things that we have yet to do, we've got to make sure that we seal this opening up. Now the refrigeration lines come out. You can see them down here in the lower left, but this is big enough for a mouse to get in. And if we get a mouse in there and he starts chewing on the wire, bad things can happen. So that's a detail I'd love to see that the manufacturers provide some kind of a panel that can literally seal that unit up to keep mice out of it. Now, just like the water-to-water heat pump, the performance on a air-to-water is dependent on outdoor temperature. And you can see this is heating capacity versus outdoor temperature. This particular unit is rated down to minus 22 degrees Fahrenheit. That's incredible when you think about where air source heat pump technology was even 20 years ago. But you'll see the capacity goes down significantly. If we're down around minus 20, that nominal 4-ton machine is more like about 2.5 tons. And if we go well up, we can get up into even 5.5 tons of capacity. You'll see that it also is a function of TS, which is supply water temperature. This is the temperature of the water leaving the heat pump. Just like with the water to water, you do lose a little capacity as you go up to higher temperatures, going from 95 in this case up to 130. But you'll see these lines really start to spread out on the COP. And again, it's that COP you're trying to maximize. So it's the exact same message. Keep the heat pump operating at the lowest possible water temperature to maximize your coefficient of performance, get the most energy for the least amount of electrical input. Okay. So here's a shot. This shows the two heat pumps, both connected to a common 119-gallon buffer tank. Here are the two 2-inch stainless tees. We actually looked at building a header here out of copper. It was definitely cheaper to build it out of just stainless steel tees and some close nipples. They matched right up with the 2-inch nipple coming out of the side of the buffer tank. Here are the two purging and isolation valves. And basically this is a 2-inch pipe down here. It comes up, and the split to two separate 1-inch pipes going to each heat pump is right here. So we use that T. We put an extra sensor well in there. We don't actually have a sensor in it right now, but we could have a sensor in the future. Here is the sensor well for cooling, and actually we use a well in the opposite side up here for heating control. Okay. The controls, we're going to get into controls in detail in episode 4, but right now we're operating this with a 2-stage set point control. The lead heat pump, and again, either of these heat pumps can be the lead, but the lead heat pump turns on when the buffer tank temperature drops to 100 degrees Fahrenheit, and it stays on until the buffer tank temperature gets up to 110. And of course, we can change both the on and the off setting if we want to. We can change the differential. Now, the lag stage, the second stage, at this point comes on if the buffer tank temperature drops to 95 and it continues to run until the buffer gets up to 105. And again, picture this bar. You could stretch this bar all the way up here if you want to. We could lower it. We have complete flexibility on the both the on temperature and the off temperature on these. And honestly, I don't know what is optimal. These are the settings that we started with for the first season. They're working well. When we get to episode 4, I'll show you in spreadsheet modeling that there is a significant difference in performance if we can lower these temperatures 5 to 10 degrees Fahrenheit. And I'm sure, actually, one of the questions we got from last week, why not use outdoor reset control? Well, we could, but one of the loads on this tank is domestic water preheating. And if we use outside reset control and we allow the buffer tank temperature to get cooler as it gets warmer outside, no problem on the heating side, but we are losing less and less preheating effect on domestic hot water. And again, they're probably thinking mathematically there's some optimal condition. I haven't found it yet. We'll find it eventually. We'll experiment with it. And we could switch this over to outdoor reset control quite easily. But I just want to explain why we're using set point control and the fact that we have a domestic water preheating load. And we're trying to get the majority of the domestic water energy from this buffer tank. That's where we selected the range we have right now. Okay. Now, from a control standpoint, over here, we're using, it's a Tecmar 152 two-stage set point controller. It could be any two-stage set point controller. It's got 2 normally open relay contacts that one is first stage, one is second stage. And as we wired this over to, here's the water-to-water heat pump, and here is the air-to-water heat pump, we used a 4-pole double throw switch, and this is what it looks like. And you can buy these online. They're not expensive. It's an industrial switch. One of the things I'll stress to you if you use this switch, make sure you pay attention to the numbers on that switch. When you look at the bottom of that switch, you're going to see very small print, but there are numbers, and we put those numbers right onto the schematic. We also put nominal 10-inch pigtails with insulated connectors onto each of these before we put the switch in the control cabinet. Trying to get into a control cabinet and wire 12 terminals on a switch like this is virtually impossible. You just cannot manipulate your screwdriver and your eyeballs and coordinate that to the point where you can get all these on there. So we put insulated pigtails on all these. We numbered them all. So once the switch is inserted into the control cabinet, we can just find the pigtail that's, for example, lead number 7 and take it from there. So that switch is what determines which heat pump goes first. Most of this winter, I believe, well, we changed it up. We had times when we let the geo do the lead and the air to water was the follower or the lag stage. And as I say, just flip the switch. And that could be done automatically. We decided we didn't need the complexity of doing that. And we really we weren't trying to necessarily equalize the hours of operation on each heat pump. Again, I think in systems that have 2 heat pumps, there probably is an optimal way or an optimal algorithm that would say, well, under these conditions, use the geo heat pump. Under other conditions, use the air source. For example, in the fall, the earth loop's pretty warm, probably about 60 degrees. If it's 40 degrees outside, it would make sense to source the heat pump from the earth loop. In the spring, when the earth loop might be down to 30, 35 degrees and it's 45 or 50 degrees outside, the air source heat pump very likely would have the higher COP. I'm not sure if we'll solve that optimization problem in my lifetime. Probably are some people working on that, but it's all good to think about. So this is actually a pretty simple control method to lead, lag, stage it. And of course, you could do this with other heat sources as well.
The one question I thought was a good question is what you pre-charge the expansion tank at for the earth loop.
Oh, pressure-wise?
Yep.
I think we're right around the nominal 12. If I go back to that slide real quick, our expansion tank is pretty generously sized, and again, Hydronic's number. Hydronics. Bear with me. I'll find it. Number 9 has got the information on the expansion tank. This is an Extrol 60 in there. One of the things that you will find with a geothermal loop, and you would also find this with a solar thermal collector system that's operating with antifreeze, you fill this loop up at maybe 55 or 60 degree fluid temperature. There's going to be times when that temperature actually gets colder than that.
Right.
And I did the math on this, and it actually isn't a big effect. What I would suggest to you is put a couple extra, pump a little bit more fluid into it. If your static pressure is not nominally going to be, let's say 12 psi, you might pump the tank up to 14 or 15 psi. And what you're doing, you're pushing a little extra fluid into that tank so that when that loop is at its coldest, you're not going to cause the diaphragm to be fully expanded against the shell of the tank. And if that happens, that's where the pressure will drop essentially immediately and instantly, and you could cavitate the pump. I actually have got some math on that. If anybody's interested in it, you can make calculations on it. But I would say from a practical standpoint, just pump a little extra fluid into that. If you want that loop to operate at a nominal, I'll say 15 psi, so pump it up to maybe 17. The other thing that adding a little extra fluid at the commissioning does, you're going to be burping some air out of that loop. That air separator is going to be capturing some of that dissolved air, and your pressure, just like it would in any hydronic system, is going to drop a little bit as that air comes out of solution. This does not have any kind of an automatic makeup on it. So putting a little extra fluid in that tank at that point is going to compensate for that air loss. And at this point, we've not had to add any fluid to the loop. We've been watching the pressure. It's quite stable. It's again, I haven't looked at it in 2 or 3 months now with the the COVID situation. I haven't been over there, but I think it was right around 15 psi the last I looked at it.
Okay, I think, Siggy, we went through that exercise with solar thermal. You have the same issue with quite a temperature spread on the
Big
not as
time
much volume typically, but a huge delta T from when you might fill up a solar system on a 70-degree day, and it can go, well, in your area, well below zero, I guess. So you've got a big. One other good question here too, Siggy, about the glycol, and I think this varies from brand to brand. He said, is there any concern about bacteria at that low percentage mix ratio? And I know Dow in their engineering book gives a low percentage number where you have to be concerned about bacteria growth in there, or you can put additional inhibitors in there. But I imagine you addressed that with when you selected the brand and the mix.
Again, if memory served me on it, I think 20% was their absolute minimum. We went with a 25% solution. It's kind of a balance. Again, we've got quite a bit of extra pipe compared to if you do a standard IXPA earth loop sizing calculation for this heat pump, we probably could have done 3 loops instead of 4 loops. So our loops are we're probably going to bottom out somewhere in the mid 30-degree Fahrenheit range, as opposed to bottoming out at maybe 30. So we didn't want to put extra antifreeze in, but if you had a particularly severe winter, you had a lot of operating, let's say we're going to keep the garage on for a high percentage of the winter, that definitely would pull that loop down more. So we decided on a 25% solution. I'm not aware of any issues with it as far as any bacterial growth, and most of the materials that are in that earth loop, it's a stainless steel pump, it's plastic pipe, it's copper pipe. I'm just trying to think if I don't think there's any ferrous metal in that earth loop at all. So, from a corrosion standpoint, there's really not much there that we do really need the corrosion inhibitors to work for.
Yep. Okay. You want to do a couple more?
Sure.
I think we got a little time here. All right. Devin's asking, have you looked at the comparing, I think you talked about this a little bit, the air source heat pump COP chart over the ground source, determine the lead lag switchover? I think you said you're working on gathering some data.
Yeah, well, that's a good question, and understanding the idea that there's going to be times when the GL heat pump would have the advantage over the air source and vice versa, and literally that can flip back and forth, and you've got to look at not only the performance of each of those machines, but also what are the water temperatures that the system needs at that point, and what's the outside temperature and what's the earth loop temperature. So there's a lot of variables that come into it. I don't know if anybody's actually done any formal research on that. One thing I will tell you, if you go back and look at those graphs, that air to water heat pump actually can perform, it can hang right in there with a geothermal as far as COP. And remember, the COPs on water to water heat pumps don't necessarily include the wattage to run the earth loop circulator. There are some ANSI standards that have a correction, some nominal value. I've looked at that and found that in general, that correction is not, it doesn't generate, the correction factor doesn't give you a number in watts. That's necessarily what you're doing with pumping that earth loop. Some of these earth loops have got over 1,000 watts of circulator power. And that's where, obviously the customer's paying for that power. It's not necessarily being reflected in that COP graph. Whereas on the air to water, the fan power is reflected into that. So the COP on that air to water heat pump, they're really starting to approach the geothermal heat pumps in terms of COPs, and doing it at a fraction of the cost. Obviously, the air source heat pump, you don't deal with the need to have any kind of an earth loop.
Yeah, and speaking of cost, I don't know, something you might want to share privately. Somebody asked what the whole budget was for a system like this, but obviously this was as much a test bed as it was a customer installation, so you can address that one.
Honestly, I don't have a bottom line on it. We were very careful when we went back and assessed this for the federal tax credit. We only included materials that would be relevant to the geothermal system. We didn't, for example, the panel radiators and the floor heating they aren't supposed to be counted, and we didn't. But yeah, some of this is materials I had, some of it's materials that we had it, obviously we got it at some good pricing in some cases, many cases. So this is probably not a system that I would design for somebody, but we had opportunity to put both heat pumps in there, and we took advantage of that opportunity.
Yeah. What about a blower door test? Was that performed on your in-house?
It wasn't. It wasn't. At some point in the future, that might be something we want to do. I will tell you that right now, my son-in-law is monitoring radon. It's a little higher than what the EPA recommendation is. So he is going to put in a radon mitigation system. Just one of the things we did do, fortunately, we have footing drains inside and out, and it's all embedded in number 2 washed crushed stone. So we have a good porous sub-slab material that we can easily tie to a floor drain and basically put a small fan on that is going to keep a slight negative pressure on those footing areas and the area under the slab. There is a complete poly vapor barrier under the concrete slab, and we're convinced we can bring that level well down. So we do have that in the works. In fact, that's probably next weekend's project. We also have fans in all the bathrooms and fans in the kitchen as well, but there is no air-to-air heat exchanger or heat recovery ventilation system in there. The air quality was good this winter. I kept an eye on the windows under really cold conditions like -10, -15. Very, very minimal signs of any condensation on the glass. And that's atypical for a new structure. And in a new house, especially one built in the fall, there's a lot of moisture in that house, not only in the wood, but in the drywall, just in materials in general. There's probably several hundred gallons of water. It sounds unbelievable, but there's a lot of moisture in a new house. And normally in the first winter, very cold days, you will see condensation on windows that you wouldn't otherwise see. These were triple glass with low E. They stayed virtually condensation free even under the coldest conditions. So moisture wasn't a problem.
But John, I think we've got most of them, and we will have John take a look at the questions that weren't answered We got to most of them, but we will get back to you, so watch for that, okay? But John, thank you. And Dan Ashington, we appreciate you from BNP Media. Bob, you rock as usual.
Great job.
And hopefully we'll see you back here next Tuesday, same time, and we'll get into the heat emitters. So thank you all.
Thank you, John.
Thanks, John.
Bye-bye now.
Yep, bye now.